all the participants except the speaker, so that there won't be any disturbances. Okay, good morning to all the KPA members, other invitees and students who are attending this webinar today. As you know, we have been conducting this webinar since last year with the idea of informing our members about developments in various fields in a very comfortable manner. Sitting in their home, they can come to know about developments, various fields, and that should help them in their teaching and also discussions and research and so on. That's our motivation. And we are very fortunate that many people have come forward to deliver the talks. People from colleges, universities, institutes, they have been kind enough to spare their time and participate in this series of webinars. And they have been very successful and appreciated by so many people. And we want more and more students join and take the benefit, get the benefit out of these talks given by experts in the fields. And I hope that will happen soon. So with these few words, I would like to welcome all of you once again, and in particular today's speaker, Professor Rudraswamy, who is a very active member of the association, as you know. Most of you know about him, but before I request him to give a talk, I'd like to give a brief introduction to his academic career. Professor Rudraswamy got his BSc, MSc, and PhD all from Mysore University. And he has got a very unique experience of having served in many colleges. He has served in the Government Polytechnic College as a lecturer, and private engineering college as a lecturer, and a pre-university college in Channapatna as a lecturer, and a first-grade college. A very, very unique set of experiences that he has had before joining Bangalore University as a lecturer, and then moving on to become a full professor and retiring in 2018 as full professor. So he has a total teaching experience of 34 years and a research experience of 26 years, more than 26 years, and published more than 130 research papers in refereed journals. He has guided 10 PhD students and 3 MPhil students. And he has visited several countries and presented his talks or papers like Portugal. He has gone to Portugal, USA, Australia, UK, Spain, Japan, and Sweden. Very widely traveled academicians. And Nucleonic Best Prize Award was given to him for the research paper entitled Breath-Stalling Dose of Therapeutic Beta Nucleides in Bone and Muscles in the year 2012. He has completed 2 major projects, one UGC major project on nanoferrite materials, and another DAE BRNS major project on compilation of experimental nuclear reaction data using X4. He is a member of several societies like the Indian Society for Technical Education, life member of Indian Society for Radiation Physics, member of International Society for Radiation Physics, London, and so on. And he has served as a resource person at several refresher courses and workshops, and has served as the coordinator of DAE BRNS sponsored workshop also. And he has, of course, done teaching work in many institutions apart from Bangalore University. And he served as guest faculty also in the newly opened Bangalore City University. So with these few words, I now request Professor Rudraswamy to take over and give his talk about accelerate in physics. Over to Professor Rudraswamy now.
Okay. Sir, thank you very much, sir. Professor Basuraj Kagli is a strong supporter of science, education, and striving hard to promote science development around the clock. So this is my 3rd online talk in the series under the Karnataka Physics Association. I'm thankful to Professor Basuraj Kagli and all KPA members for this opportunity. I am also thankful to Professor Srivatsava for joining online, and also Professor Kenneth, who is now presently is in USA. So I'm thankful to both of them. I'm also thankful to Professor S.V. Raman and Dr. M.K. Raghavendra for providing YouTube and Zoom platforms Okay, so I will begin with my first slide. So particle accelerators, hub of talents. Particular accelerator is a machine that uses electromagnetic fields to propel charged particles to very high speeds and energies to contain them in well-defined beams. Particle accelerator. So these are the accelerators I will touch upon. So you can classify them as electrostatic based particle accelerator, cathode ray tube, voltage multiplier, voltage generator, Van de Graaff, Cockcroft, Walton. So these three come under electrostatic field based, and time varying electric field are based is a linear accelerator, Alvarez Linac, cyclotron, betatron, synchrotron, synchrocyclotron, strong focusing Linux. So these are the things, say accelerators I will touch upon. So first of all, say now I will take up cathode ray tube. So I will just okay. See, this cathode ray tube it's a well-known thing to all physics people. Cathode ray tube is a particle accelerator which accelerates electrons to kinetic energy from 0 to 10 keV to travel between cathode and anode, maintained with 10 kilovolt potential difference and 10 to the power of -4 atmospheric pressure of gas inside glass envelope. Modern cathode ray tubes can handle voltages up to 55 to 60 kilovolts. So inventors of cathode ray oscilloscope. The first brand invented cathode ray tube in 1897 and introduced the fluorescent screen to name it cathode ray oscilloscope. Thomson discovered electron in 1897 using cathode ray tube. Roentgen discovered X-ray in 1895 accidentally using cathode ray tube. So Cockcroft-Walton voltage multiplier. So Cockcroft voltage multiplier is a circuit used to convert AC to DC voltage and consists of series of stages. Each consists of 2 capacitors and 2 diodes, which doubles voltage and operates in the range of 200 to 1000 kilovolt. So Cockcroft voltage multiplier, you can use it as a particular accelerator. The first figure which I have shown here, in fact, both Cockcroft and Ernest obtained, awarded with Nobel Prize for this machine. So together, this Cockcroft voltage multiplier is used as a particle accelerator to accelerate proton to achieve kinetic energy of 700 keV to bombard with lithium to produce alpha particles in 1932. So this, I think this is the first experiment carried out to split the atom, lithium atom into alpha particles. So, the second figure I have shown, see, this is a original Cockcroft-Walton multiplier used as a particle accelerator to help in the development of the atomic bomb in 1937 and currently present in the National Science Museum, London. Coming to Van de Graaff voltage generator. So we are all familiar with the Van de Graaff voltage generator, and inventor is Robert Jemison Van de Graaff, American physicist, noted for his design and construction of high voltage Van de Graaff generator. Okay, see, in this Van de Graaff voltage generator, it uses a moving belt to transfer charge from low voltage area to the high voltage hollow metal structure, allowing for acceleration of various particles such as protons and alpha particles. Original Van de Graaff voltage generator, he was capable to produce potential difference of 80 kV in the year 1929. Improved version of Van de Graaff generator. So after, first comes is Pelletron accelerator. This Pelletron accelerator uses a chain of metal plates to change a terminal voltage, terminal to a high voltage, allowing for more stable operation. BRC TFR Pelletron accelerator with a 14 MeV terminal voltage can accelerate protons with energies between 8 and 28 MeV in Inter-University Accelerator Center, Delhi. With 15 UD pelletron can accelerate various ions to energies up to 200 MeV. So coming to tandem accelerator, see here, okay.
Excuse me, please go slowly and explain each one of them because you are going too fast.
Okay, right, sir.
With respect to the figure, explain the things. That will be
Okay.
easy. You're going too fast.
Right. So this, pelletron accelerator and the difference between pelletron and Van de Graaff is see, structure-wise it remains same. Only thing replacing is metal plates. There in Van de Graaff, original Van de Graaff uses insulated belt. But coming to pelletron accelerator, that belt, isolated belt is replaced by metal pellets, chain of metal plates. So that way you can increase the voltage capacity on the hollow sphere, and also you get a better stable operation. See, this is how it is designed. Pelletron, it is based on Van de Graaff. Coming to tandem accelerator, so what happens is you can say use the same hollow sphere you can make use of. And here at one end, you can use a source producing negative ions. So you can always accelerate these ions. Once produced here, ground potential here. This hollow sphere, it is at positive potential, and this is at ground potential where ion source is placed. And on the other hand, see, you can think of another end you can think of. See here, what happens is the negative ions, in fact, produced by this source will accelerate towards the positive terminal. So then what happens here? Your positive ions, you can able to strip off 2 electrons, and that way, that the negative ion you can convert into positive ions, and thereby what happens is it gets repelled by this positively hollow sphere and moves to the other end. That way, you can accelerate twice the same ion. You can accelerate twice by this method, and total energy gain for a proton is double terminal voltage. See, in fact, see 30 in a tandem accelerator. Suppose the capacity of the hollow sphere is 35 megavolt. Then you can accelerate using the same device. You can able to get the energy 70 MeV. So that is the thing you can get. So this is the advantage you get in tandem accelerator. So it is also originally it is improved version. See, that is what happens. So coming to the next thing, linear accelerator. Linear accelerator is also called as LINAC. So see, what happens here is LINAC actually consists of source. See, this is the source used. Of course, you can use both for producing positive ions and negative ions, electrons. So LINAC consisting, this is the source position, and you can produce ions, variable ions at this point, and you can pass it. See, these are the tubes, drift. They are called as drift tubes. In fact, lengths, are in fact increasing here. So, and it is the ions, in fact, are passed through these drift tubes. And also one thing you have to understand here: drift tubes, these alternative drift tubes are connected to see, this RF oscillator. The alternative tubes, the first, third, fifth. Likewise, there are n. If you have n number of tubes, you can connect to one end of the RF oscillator, and even tubes you can connect to the other end of the tube. And see, in fact, these drift tubes work in pi mode. Works in by, what do you mean by pi mode? See, electric field. See, this is the electric field, and this gap and this gap. If you take, electric field will have a opposite phase. Suppose this is has a positive phase, then this will be a negative phase because they are connected alternatively. So that is called pi mode. And what happens is the entire thing, system is kept in a vacuum to minimize collisions between ions and air molecules. Synchronization occurs. In fact, this is an important concept, used in linear synchronization. See, what do you mean by synchronization? See, in fact, when ion travel, it travels, it travels, in the first two means its travel time should exactly be equal to half period of RF oscillator. See, even and if it is equal, then that phenomena is called as synchronization. The travel time taken by the positive ion should be exactly matched with the half period of this thing. See, then only what happens, it comes out. Okay, see, it comes out here. Okay, this is in negative. If suppose this gap is negative in phase, it can positive ion can traverse to the second phase, second thing, and here it is positive. So by the time say this travel time, if it is the half the period, then this positive phase, will change into negative phase. That way, it can accelerate to different phases. And of course, why the tubes are increasing length? It is because the velocity keeps on increasing because accelerators are meant for increasing the velocity of the ions and to increase the kinetic energy of the ion. So velocity as it increases, and your length should also be increased. Otherwise, your synchronization will stop. Will destroy. That's why it is required. And in fact, highest energy. Highest energy what you can achieve with the original LINAC. Say for proton in 1947 is 31.5. And in 1970, it was 70 MeV in 1930. Of course, you can use this LINAC to accelerate even electrons. With some modification, you can accelerate to get the kinetic energy varying between 60 to 30 MeV. See, this is about the construction of LINAC. Coming to the theory part, I don't want to give much of the theory here, but this is required, how it performs. Dependence of kinetic energy on length. Why length should increase with the increasing of order. Kinetic energy, in fact, see, this is how we can write down kinetic energy formula. This is how we can write down. And here I have written kinetic energy in terms of potential difference. This V actually represents the potential difference between any two successive tubes. Any two successive tube, it remains constant. Okay. So so you can equate these two, and finally you can write down velocity of the ion in the nth tube. Say acquired. What is the velocity acquired? You can write in terms of this formula. Of course. So that this thing Vn this Vn square, I'm just substituting here, and that way here all the except n both are constants. That way you can say En is proportional to n. As the order of the tube is increased, kinetic energy also increases. Synchronization is an important concept used in this thing. So therefore, your length of the tube, any length of tube. Should always be equal to velocity of the ion traversing in nth tube multiplied by the half period of the oscillator. This is the traveling. This is also the traveling time. So I'm just substituting this value here. This substitute here means you can finally work out kinetic energy acquired in terms of length. It depends. Ion kinetic energy increases with increase in square length of the successive tube. This is the important design. When you're designing a LINAC, so this you must take care of. Then you can achieve synchronization. You can achieve kinetic energy. You can increase it. So without synchronization, you cannot proceed. This is about LINAC. coming to Alvarez LINAC, it is an improved version of LINAC. Of course, what is the one difference you get here is, see, this is your cavity, a cavity chamber. The whole thing is cavity chamber. It is connected to, these two ends are connected to the RF oscillator, opposite ends of the RF oscillators. And these are the drift tubes. So even in other LINAC, we'll have this same kind of thing. Only difference between the Alvarez and other LINAC is these drift tubes are not directly connected to RF oscillator. It is connected to this thing. So it has some advantages. Alvarez, in fact, American Luis Alvarez is an American experimental physicist who was awarded with Nobel Prize for Physics in 1968 for work that includes discovery of many resonance particles having extremely short lifetimes and occurring only in high energy nuclear collisions. In fact, Alvarez, as I said earlier, Alvarez LINAC consists of resonant cavity chamber whose ends are connected to opposite ends. Of course, you have the spatially separated drift tubes. In fact, it is hanging inside the chamber. Okay, once your ion is passing through the chamber, and your ions will get shielded during deacceleration process. Okay, it is the deacceleration process. It gets shielded. It doesn't come out. Once phase is changed between the gap between the tubes, it comes out and moves. It moves forward with increasing velocity and kinetic energy. It works in zero mode. That is, electric field at a given time has same phase in each gap, whereas some other LINACs work in pi mode. Of course, see, both the cases you can use both to accelerate ions. Of course, advantages of Alvarez LINAC over other LINACs. In fact, additional feature is quadrupole magnet is placed in the nth drift tube. Provides, in fact, in all tube, last tube is selected and quadrupole magnet is placed in nth drift tube. Of course, I will explain this quadrupole magnet feature at the end, its importance. Okay, and of course, this is one advantage. If you make use of quadrupole, you can get a transverse focusing. That is one thing, one advantage. It is always be there in Alvarez LINAC. Quadrupole magnet is always be there. That is one advantage. Focusing. Heavy ions can accelerate to high energy, which is impossible with some other LINAC. This LINAC, Alvarez LINAC is used as a pre-accelerator to boost ions energy before injecting them into synchrotron. Of course, I will come to synchrotron next. Next highest energy achieved for proton was 100 MeV. In other LINACs, it was just 70 MeV. That too in 1945. It was, but with this, it is 1947. That also able to achieve energy, highest energy 100 MeV. So this is about the special features of this Alvarez LINAC. So coming to Stanford Linear Accelerator Collider. In fact, based on this LINAC principle, it is built actually. Stanford Linear Accelerator Collider, SLAC, is name stands for Stanford Linear Accelerator Colliders. Of course, it is situated in Stanford. That's why that center is called CC. So this is the structure of Stanford Linear Accelerator. So it is a 2-mile long linear accelerator. So, okay, consists of electron source. Consists of electron source. This gallium arsenide photocathode is used as a electron source, which produces the energetic electrons and interact with the tungsten target. The tungsten target, in fact, this electron will go like this. And here you will have a tungsten target, and it interacts with the tungsten target and produces positrons, so which are then guided by a magnetic system to collect as a E plus source. Of course, here green and blue are distinguished here. Blue is meant for electron movement, and E is meant for positron movement. So they are extracted from the damping rings. Here, see, they're collected here, and then they're taken out from this damping ring, and both of them are made to accelerate in opposite direction. In opposite direction. See here, see, this is how it comes here. Electron beam comes like this, and your positron goes like this and collides here at this point, and collision takes place. Of course, you can use a detector here. This is the detector part. You can watch the event. Of course, you can detect the event, and using this quark, this collider, it was possible to detect charm quark in the year 1974 and tau lepton in the year 1975, which led to the development of quark and standard models of particle physics. Of course, see this, and next, large electron positron collider, LEP, at CERN, Switzerland. It was later developed based on the design and technology of this Stanford Linear Accelerator Collider, whose research has led to 4 Nobel Prizes in physics. So this is about Stanford Linear Accelerator. So of course, I'm say nice to know that our distinguished KPA member, Professor Sharana Basava M. Kenneth, visited Stanford Linear Accelerator Collider Center on 17 March 2025. Thank you, sir, for visiting Stanford Center. Coming to cyclotron, you find 2 spatially separated. See, these are the 2 circular Ds. Okay, hollow disk. Ds placed in a vacuum chamber are kept between, these 2 are kept between 2 electromagnetic poles, which provide a magnetic field. Perpendicular to the planes of Ds. It acts perpendicular to the Ds, which are, and these are connected to opposite ends of the RF oscillator. And the positive ions, source is placed here. The positive ions released from particle source located the center. See, this is the position. Center of Ds are attracted to 1D. See, positive ions, when it attracts, when the this D is has a negative polarity. It attracts, and what happens? It accelerates. It gets attracted and goes into the D, accelerates in a semicircle. It rotates in a semicircle, and by the time it emerges out of this D, this D becomes negative polarity. Earlier it was in positive polarity. Now, because it gets negative polarity, it gets attracted to the other D. Again, it performs a this circular path, of course, with increasing radius, because as long as every time velocity keeps on increases. That way, it gets a semicircular path, and this will continue. And of course, one important thing what we have to follow here also is synchronization. Synchronization is important. What do you mean by synchronization? RF frequency. This thing, you see an oscillator. See, it has some frequency. You can always fix the frequency is fixed here. In fact, in cyclotron, frequency is fixed. And see, this ion is rotates in a spiral path, and of course it comes out later on, and it's on the target. And you can work out for this ion also what is the frequency of revolution. This frequency and this frequency should exactly match. Then only it can attract to the other D. Otherwise, it doesn't it doesn't attract, and your ion doesn't accelerate. That problem you faces. That's what is called synchronization. Frequency, the RF frequency is in synchronization with cyclotron frequency. Cyclotron frequency is nothing but the angular frequency of revolution of the ion, in which ions are accelerated in spiral path to emerge out finally with highest energy. Of course, finally it emerged out with highest energy. Highest energy achieved for proton was only 25 MeV in 1930 due to relativistic limitations. It has some limitations. You cannot use this cyclotron beyond 25 MeV. Of course, later on, see I tell you why. See, there is a relative limitation in the next slide. In fact, this is invented by inventor Ernest Lawrence. Okay, he was an American physicist who received Nobel Prize in Physics 1931 for his invention of cyclotron. In fact, see the basic formula you can make use of and work out what is how energy depends on radius. Okay, see Lorentz force. In fact, it is ions moving in a circle is subjected to magnetic field. So that way you can use this formula. Lorentz force equals centrifugal force, and this is the formula you can write down. And you can write down okay, expression for R and as well as for velocity of rotation. And kinetic energy you can work out, just substituting for V here. This is what you get it. And here the kinetic energy depending on the radius. So highest radius, if the ion is attained, then energy is also highest. So while coming out, okay, with depending on the radius, you see this energy also becomes highest. So that way, see, I am writing here A is proportional to R square. So it is mainly depends on the cyclotron. Energy is mainly depends on radius square. Okay, so and of course you have to maintain constant magnetic field is constant. It is used only to get the particle to revolve. See, of course, this principle is used constant magnetic field and is used not only for cyclotron, even for synchrocyclotron. This I will explain it later on. See, of course, both in both the case you get ion path spiral. This principle is used, but only some advantage. Synchrotron, cyclotron has some limitation, relativistic limitation. Okay, of course, see here it is the energies are not only depending on B and R, it also not only depending on R, it also depends on B. So that way, in case of synchrotron, you can keep R constant and you can vary magnetic field. That way you can increase the energy. So by keeping R constant and varying magnetic field, you can get a desired kinetic energy. So this is for constant R applicable to C. This is applicable in synchrotron because R is constant here. So the ion path is circular in synchrotron. So, but there is a difference between both synchrocyclotron and synchrotron has have advantages over synchrotron. That I'll come to it later on. So coming to relativistic limitations of cyclotron, this is the period you can work out for ion revolution. See, this is a ion revolves in orbit period you can work out, and okay, and you can even work out the angular frequency. That is called cyclotron frequency. This is for ion. It is not for RF oscillator frequency. See, this is the one you can work it out. Of course, in relativistic case, what happens is this is well-known thing. Mass, mass is depending on velocity here. See, if, as the ion is moving with higher and higher velocity, your mass will increase. Your mass will increase. So that way, here what happens is the M. You can just look into M and omega here. So here M increases, of course, with increasing the relativistic velocity, M should increase and W should decrease because W is depending on inversely proportional to M. So that way, in cyclotron, what happens? See, frequency you cannot vary. It is always fixed. So that way, here, what happens is this is varying. In fact, this cyclotron frequency is reducing, in fact, with relativistic velocity. So that way, if this is not matching with cyclotron frequency, naturally your ions will deaccelerate. It doesn't get into the other Ds. It gets deaccelerated. That problem you faces. It is only applicable for non-relativistic case. Relative case, it is impossible. So, but coming to synchrotron and synchrocyclotron, what happens is, your frequency, RF oscillator frequency can vary, very, very, okay, to according to the decreasing of cyclotron frequency. So, and thereby you can achieve ions and electrons to accelerate. So this is the, of course, I will come to the details later on. So coming to betatron, see betatron, okay, it is ruled out. Electron, acceleration, achieving acceleration, achieving energy for electron is ruled out because its mass is very low. It experiences, electron experiences a relativistic effect at the early stage itself, because mass is so small. So that way it is impossible to make use of at least ions. You can use it up to 25 MeV, but ions, electron, even 10 keV, once you reach, see, deaccelerate because of relativistic effect. So to overcome this problem, see, this William Kirst has invented a different kind of device called betatron. It has a downward chamber. This is a downward chamber. Of course, it is positioned between two electromagnetic poles. Of course, driven by AC. In fact, AC is important here. Driven, due to which what happens, magnetic field is sinusoidal in nature. In fact, magnetic field keeps on varying with time, and your downward is in between these two poles. Electrons, of course, you exclusively use for electrons only. Okay, electrons from the gun, is shot into downward at start and removed at the end of every first quarter cycle. So only first quarter. See here, this is the alternating current, is used here. Only first quarter cycle, when it is subjected. Okay, when the magnetic field is varying first quarter cycle, electrons will be shot at the start and removed at the end of every first quarter cycle. See, once your alternating current reaches this value, it is get removed only because acceleration only happens during this cycle. Okay, because during this cycle, flux grows from 0 to its peak value. For all other cycles, magnetic flux is decreasing. That doesn't help. So that's why, see, you have to take care of this thing. So see, this is actually down. This is schematic diagram. So see, this is the actually magnetic field, sinusoidal poles, electromagnetic poles. So betatron was the first successful machine used to produce electron beams with energies beyond the capabilities of electron guns, and to accelerate electrons to energies up to 300 MeV. 300 MeV, it was not even possible with cyclotron 10 keV. So, but with this, you can get, this was a significant advancement at that time. So, he was an American physicist, worked on advanced particle accelerate concept, and of course, betatron. So he is awarded with a different prize. Okay, and coming to the condition, see, important. What is required is betatron condition. Is important. Betatron utilizes sinusoidal magnetic field. As I said just now, see, you are making use of a magnetic field, sinusoidal magnetic field. So what happens with this magnetic field? It treats the electron to move with a velocity v in a constant circular field, because you have kept the downward between the pole piece, and magnetic field is acting vertically. It is as soon as you inject the electron, it goes in a constant orbit, constant circular orbit, moves in a horizontal plane. Of course, radius I have put it as r. So, and that principle, as usual, you can write this Lorentz force, this centripetal force, and you can write this equation, and you can even write the MV, the E B dash R. This is nothing but momentum. This is nothing but momentum. You can work out what is the force exerting on this electron moving in an orbit. That is what I have worked it out. And here I put pi dash. Here I am replacing B dash as pi dash by pi r square. This is flux divided by pi r square is magnetic field. What is the pi dash? It is actually magnetic flux density corresponding to B dash, which is the magnetic field acts at circumference. It is important. Circumference of circular orbit. So that is important. Flux density is also acts at the circumference. Coming to another advantage of sinusoidal magnetic field is it treats electron as a current loop. In bitetron, we are not at all making use of electric field here. We are using a current. The magnetic field, varying magnetic field, it treats electron as a current loop to induce EMF V equal to the rate of change of magnetic flux. And you can write down V equals d pi by dt, work done like this. Force you can work out by work by distance. This is what you get it. And both forces you can equate. And finally, you can write, of course, this pi, what I have written, this pi is different from this pi dash. This is the actually average magnetic flux passing through an area enclosed by the orbit of radius r. It is passing through the. It is not the flux passing at the circumference. It is passing through the area enclosed within the orbit. So that way you can integrate, and finally you can relate these two fluxes like this. Pi equals 2 pi dash. So that is what I have written here. If the average flux density passing through an area enclosed, if this condition is not met, the electrons will spiral outwards and inwards, losing control of their trajectory and prevents them from this thing. Okay, coming to relation between, you can work out kinetic energy and magnetic field. Now, the sinusoidal magnetic field, plays a role in deciding the kinetic energy. In fact, sinusoidal magnetic field, this is how you can write down. Okay, this is the sinusoidal as it I have worked out. So electron in first quarter cycle, electron revolves in a electron, and energy you can work out. Energy gained you can work out. Just making use of this formula, E into V. Of course, V you can write as d pi by d. Of course, minus is not considered here. The magnitude is important. So that I have worked out. And you can work out mean energy gain in one revolution. Okay, in first quarter cycle, how much energy electron gains, that you can integrate and divide by T by 4, because only T by 4 is important here. So that you can write down, finally you can write down in terms of peak value of the magnetic field, total path traveled. In fact, in betatron, electron revolves at the velocity of light. So that's why velocity into time taken to complete one revolution, that is T by 4. I worked out number of revolution also. See, you can work out dividing total path travel divided by circumference of the circle. So I worked out, you can work out maximum kinetic energy. Now you can work out number of revolution performed, average energy per revolution you can work out. You can write down E max in terms of B dash max RC. In fact, B dash RC is nothing but P. B dash max is nothing momentum. In fact, it is there in previous slide. Condition. So in fact, your Emax depends on B dash. B dash is the peak value of B dash. B dash is the magnetic field at the center. So or even you can express in terms of P max. So this is how it is designed. Coming to synchrotron. Synchrotron, so see, this is the construction of synchrotron. In fact, see, this is what it is a special type of cyclotron. It utilizes increasing magnetic field. See, this cyclotron utilizes increasing guiding magnetic field and decreasing RF oscillator frequency. So here, one magnetic field is increased and kept, and radius circle, constant. It will and radius is kept constant. RF oscillator frequency, it is decreased. You can always decrease in synchrotron, and thereby what happens? You can synchronize with decreased cyclotron frequency. In fact, it is useful. This machine is useful for relativistic ions. So those ions moving with relativistic speed, you can without any problem you can use this. So there is no limitations here. So you can increasing due to cyclotron decreases because of increasing relativistic mass of ion to accelerate relativistic Okay, so that problem you can overcome by varying the frequency. Of course, there are two colliders, Large Hadron. See, Large Hadron Collider is well-known thing. It is in CERN, Switzerland, and Tevatron, Fermilab, USA. Yeah, is in USA. They are the two special types of large synchrotron used to collide particles. Okay, of course, this cyclotron uses the injection. Many things are shown here. Injection system, then booster ring. It consists of seven many parts. Then comes is storage ring, bending magnet, then insertion device, optics hutch, experimental hutch. Okay, these are the things. Of course, they have shown here in detail insertion device. So that you see that you can understand here. Injection system is used in synchrotron to pre-accelerate ions. See, you can always make use of accelerate ions. Okay, before sending into booster ring. It is that booster ring again accelerate further and increase the strength of the ion. Storage ring, of course, you can send the ion to storage ring to circulate high energy ions, and it serves as a source of synchrotron radiation. In fact, storage ring, okay, if you make use of electrons, you can produce a synchrotron radiation. Then bending magnet. In fact, bending magnet is there, So you can use bending magnets which guides and focuses high energy ions to move in a circular orbit. And insertion device. In fact, see, this is a insertion device. Okay, it is placed between bending magnets. So this is used to as a periodic magnet. What is the structure of insertion device? It says as a periodic magnetic structure to guide electron beam to produce highly brilliant and forward directed synchrotron radiation. Of course, beam lines. So beam line is also shown here. This is a beam line. So beamline to deliver synchrotron radiation to optics which houses components like monochromators and mirrors that prepare synchrotron radiation to transfer the experimental HUD, which contains sample and detectors for experiment. So these are the people who invent. In fact, scientists have published the idea of synchrotron in a Soviet journal, 1944. Macmillan, okay, of course, he secured a Nobel Prize. Macmillan built the first electron synchrotron, 1945. So conceived idea, he gave the conceived idea. And Oliphant, designed first proton synchrotron in 1943, but which was then built in 1952. He designed by him in 1943. So this is about synchrotron. Coming to Large Hadron Collider, of course, it is in CERN, USA. See, what is the LHC? It is shortly called as LHC, Large Hadron Collider. CERN, Switzerland, is the world's largest, most powerful synchrotron. So it has a 27 kilometer circumference ring underground. The entire ring is placed underground, and that ring is traversing through Switzerland and France. And this LHC is designed to accelerate 13 TeV, tetra electron volt, highest energy in the ever produced. In the history of particle accelerator. Energy to collide. In fact, this is used. It is used to collide protons moving in opposite direction at almost speed of light. See, this is what it is done using LHC, of course, this LHC made a significant discovery of Higgs boson in 2012, which is a crucial particle in standard model of particle physics. So this is, of course, here you see this is actually is a synchrotron. Particles pick up speed in the super proton synchrotron. Of course, pick up speed equal to the speed light, equal to the velocity of light, and transfer. This is actually collider tunnel. Ring, a tunnel. It is kept underground, and see here, once it comes out, protons comes out. The protons are made to accelerate in opposite direction. And you can see 9,600 super cold magnets are used to go in a circle. This proton in opposite direction, and 4 detectors are placed. To observe the collision of these protons. This is about large hadron collider. Next comes is tevatron. So tevatron is again a special type of synchrotron. It is in Fermilab, USA, with a specific. Okay, whose circumference is, see, this is a circumference is 6.3 kilometer. It was particularly well known for its high energy collisions of protons and antineutrons. See here, the red is actually represent anti-proton direction, and blue represent for proton source, anti-proton source, proton source. You can make use of both. You can make them to go in opposite direction. And here at this point, these two protons. After acceleration, these two protons will collide, and the collision energy at this point is 1 TeV, Tesla. Its main claim to famous is discovery of torque quark in 1995. A particle predicted by the standard model, but previously, of course, so that is it was not observed earlier because of tevatron. It was observed in 1995. Of course, it is no more in operation. It is ceased to operation in 2011, primarily due to advent of LHC. See, okay, this is about synchrocyclotron. See here, of course, just like cyclotron, here also the ions move in a spiral path. Of course, it is something similar to cyclotron and synchrotron. What happens here? You will have a single D instead of having 2 Ds. You will have a single D. Of course, this target is there. You have to connect this to RF oscillators. One end is you have to connect to RF oscillator. Of course, you have to make use of electromagnet. Your D must be kept between two magnets, magnetic poles. Magnetic poles. In fact, magnetic field is constant here. See, in fact, this is about synchrocyclotron is a special type of cyclotron. Utilizes constant guiding. Magnetic field is constant here. So only your frequency, RF frequency decreases to synchronize with decreasing cyclotron frequency. In fact, your ion moving with relativistic speed, see what happens, mass will decrease. As I said earlier, mass increases. And so mass increases means its cyclotron frequency. Okay, that is ions frequency decreases. So to match, you must decrease accordingly RF oscillator frequency. That is called synchronization. That you can do it with this. So only one D is connected to one terminal, while the other is connected to ground potential. It makes no difference. You don't have to require both the Ds here. One you can connect, and of course it goes in a circle. The maximum attainable energy with synchrocyclotron is 1 GeV. Maximum energy is achieved for deuteron and alpha particles for 195 and 390 MeV respectively. CERN synchrocyclotron discovered short-lived. The pion was discovered in 1957 in CERN. They used the synchrocyclotron. Of course, Edwin Macmillan was an American physicist credited with being the first to produce the transuranium element, neptunium. For this, he shared a 1951 Nobel Prize in Chemistry with Glenn Seaborg, awarded with National Medal of Science for Physical Science, Atoms for Peace Award. Of course, coming to this is the strong focusing. Actually, principle is used in all advanced particle accelerators. Particle accelerator, quadrupole. You can achieve the strong focusing of the beam, ion beam, with the help of this quadrupole. So you will have total 4 poles. 4 poles you will have. 2 opposite poles. See here, north, south, north, south. 2 magnets with 4 poles you can make use of, and this is the direction of beam is away from the plane of the paper. That is in Z. You can call it as Z direction, and say this is y direction, this is x direction. These are the direction of magnetic field. So this is and you can see here magnetic field directions I have shown here, produced by all the 4 lines. Okay, and of course, ion is moving in the z direction, so that way you get a Lorentz force. See here, what is happening in this particular case, magnetic, your Lorentz force is acting in the vertical direction, the opposite direction too. That way you get a focusing. You get a focusing along y direction. Similarly, by making use of another quadrupole next to it, you can achieve focusing in the x direction. The same principle you can use it, but only thing is you have to make use of another quadrupole. Of course, this I have shown here for sake of information. Text to pole. Of course, they are used for more complex case. So, what is a strong focusing? So, you have to understand traditional focusing in early particular accelerator was achieved with single magnets. Earlier magnets had only single magnet, which could only focus particles in one direction, either horizontally or vertically. But strong focusing in modern particles was achieved with 2 or more phased quadrupole magnets. See, you can make use of instead of just one, you can use a quadrupole and place one after the other, and thereby you can achieve focusing in both the horizontal and vertical direction. Of course, your beam will move in the z direction. That way, you can achieve focusing in both the x and y direction, and that way you get a higher energy. Yeah, you can able to produce higher energy and intensity, allowing for longer and thus more powerful linacs. Research laboratories, USA, Switzerland, Canada, Germany, Italy, feature strong focusing average linacs. The inventor of this is Ernest David Coran. He's an American accelerator physicist and a fundamental contributor to modern large-scale particle axial concept. His most notable discovery was 1952 work. Okay, and he makes use of the strong focusing case. Of course, now almost I'm coming to end. Indian particle accelerator. I have listed out Indian particle accelerator. Baba Atomic Research Center have total 7 particular accelerator. Of course, first one 14 UD pelletron accelerator with LINAC. So it is a collaboration of BRC and TFR. Of course, you have a folded tandem ion accelerator, neutron generator, electron RF. These are the things. These are different type of particle accelerators you can find in BRC. Coming to variable energy cyclotron, it is present in Kolkata. VEC, 224 centimeter variable energy cyclotron. K130 series. It is available in VEC, Kolkata. Raja Ramanda Center for Advanced Technology Indoor. Synchrotron radiation source. Indus 1 and 2. And it can produce electron energies of 450 and 2.5 GeV. It is in indoor. Raja Ramanda. It is called as RRCAT. Shortly, it is called as RRCAT. Of course, 1.7 to 3 MeV tandetron accelerators are are present at various places. The Indian Institute of Technology, Kanpur, Guru Ghasidas Vishwavidyalaya, Indira Gandhi Center for Atomic Research, Kalpakkam, Institute of Physics, and Inter-University Accelerator. Accelerator Center, Delhi has a 15 UD pelletron accelerator. With LINAC. And Bangalore University. In fact, Karnataka, has one particular accelerator. It is called as microtron accelerator, 8 MeV. Of course, our former Vice Chancellor, Professor Siddhappa, was instrumental in establishing this microtron accelerator in Bangalore University. So it is working very well, and many of the users from all over India are making use of this facility. Punjab University has some particular accelerator. Gandhinagar, then Pune University has a. See, this is the overview of Mumbai BRC TFR pelletron LINAC facility. This is about coming. See, Kolkata Variable Energy Cyclotron Center. This is the overview of this thing. And Delhi Inter-University Accelerator Center. This is the view of UAC. So thank you very much, sir, for your patience hearing.
Thank you very much for a very detailed account of a variety of accelerators in use.
Yes, sir.
There is some time for any questions or comments. Anybody would like to ask any questions or make any comments, you can raise your hand and then unmute and ask. Okay, any questions here?
Not seeing the,
Okay, please.
I'm not seeing the hand. So let me raise it like this.
No problems. No. Ask.
Yeah. So thank you, sir,
Thank you,
for
sir.
a very comprehensive coverage.
Okay. Thank you, sir.
And this should be very useful for students who are
Yes, sir.
planning to take a career. Yeah.
Yes, sir.
Very nice. We went
Yes,
through systematically one by one. That was very nice.
Yes, sir. Yes, sir. Thank you, sir. Thank you, sir.
Okay, any other questions?
Since you are doing it so well, you should give one more on not physics but non-physics applications of
Yeah.
accelerators.
Yeah, right, sir. You're right. So it has particular accelerators have so many applications.
Yeah.
Yeah, we can do it, sir. It's not
Including medical cyclotron for
Yes,
production
yes,
of
yes.
isotopes.
Yes, sir.
So there is a question from the viewers.
Okay, please ask. What is the question?
Yes, sir. In Van de Graaff generator, why
Yes,
there is
sir.
a transition from lower voltage initially to high voltage later on?
Oh, okay. See, in fact, the charges, in order to get a high voltage, if you use a high voltage, in fact, charges, protons, suppose you want to accelerate protons, you have to start with the highest voltage to lowest voltage. Okay, plus charges first, accumulates in the dome, that way it gets a positive potential. And there you can keep protons, and thereby, because of repulsion, it goes down. Okay, and in fact, this machine, is used to transfer charges. See, in fact, it is called what is called motor. Motor, with the help of motor, what you can do is low voltage motor. You will make use of low voltage motor. You make use of, and using a belt, you can transfer charges and make all charges to accumulate on the dome. So low voltage machine, high voltage machine. See, this is how this thing is not your motor is not a high voltage machine. So that is the use of this Van de Graaff. You can't all of a sudden you cannot make use of a machine of high voltage. You have to start. Yes.
You have to increase gradually.
Yes, sir.
You have to increase the voltage gradually, step by step.
Gradually, you have to increase. Of course, it is required. High voltage point is required to next to transfer charges.
Yeah, I have a simple question.
Yes, sir.
The CERN at Geneva, is there any limit to the energy that it is able to produce for protons? Any limit? I mean, do they have? Is there any upper limit? What is the highest energy they are able to produce right now?
That is 13 Tesla electron volts, sir.
TeV.
I'm sorry.
Tetra electron volt. Highest energy.
14 is not 7. Not 13. 14. Each proton is at the most 7 TeV. It is 2 protons.
6.5. But
Yeah.
2 protons together,
collide, the total is 13.
Total energy considered as 13.
Yeah, in the center of mass system.
Center of mass system. Yes, 13. Yes, correct.
Usual protons are only 6.5.
6.5. Yes, you are right.
That is the highest possible. They cannot go beyond that.
No. It is not possible.
They cannot go at LHC.
Now that's what I'm asking. In the world,
at LHC they cannot go beyond that. But they are planning a new accelerator called Future Circular Collider, where energy of each proton may go up to 50 TeV. And therefore, the center of mass energy may go up to 100 TeV.
Where is it planned, sir? Where is it planned? Where exactly?
Same at CERN.
CERN itself. Oh, I see.
Yeah.
Okay, Professor Somshekhar, you wanted to ask any question?
Sir, we keep reading. Namaste, sir. It was a
Namaskar,
good
ಹೇಳಿ sir.
presentation.
Yes, sir. Yes.
The laser-driven particle accelerators. Oh, can you throw some light on them?
What are they? Are you aware of them?
No, I am not aware of laser-driven this thing. I am not aware.
Maybe
You see, sir, I can give you the basic idea. You take any ionized gas, it has positive ions and negative ions, and you send in a very strong laser field. So because of the electric and magnetic field, the positive and negative ions will separate. And then once they separate, they will start oscillating. And you try to see that the electrons move along with the wave. So this is called the wave field acceleration. So laser introduces very strong field, produces very strong field in the plasma, which separates electrons and
Okay, sir.
positive ions, and then the electron is accelerated.
Thank you, sir. Thank you.
And it has been experimented and is working at some places, but the proof of concept is there.
Okay.
But bigger machines are not yet made.
Any other questions? Professor Nagaraj, you have any questions? Otherwise, please propose a vote of thanks.
Okay, sir.
Sir, just I wanted to add something, sir.
Professor Kennedy is asking.
Yeah,
Yes,
no,
sir. Yes,
this
sir.
laser driven, no. Actually, in Slack they are working on that also. That means they are improving, trying to improve the lengths of accelerators, etc. The laser driven accelerators are compact in size.
Yeah, they will be compact inside.
That's what they are doing now. Instead of this 2-3 miles, it will be reduced like around 5 times less or something like 6 times less.
Sir, but still it is used along with the LINAC, right? Normal principle.
No. They
combined
are
or separate?
Separate. That means
Separate.
actually they are using this laser to activate some radio, this RF, this one, wherein they get this acceleration of the particles.
Okay.
No, I really don't know much of that theory, etc. Because
it is being
sir, what
discussed
sir,
30
professor
years.
told, you have done the linear accelerator means that tubes. Only we studied that. After going to Slack only, I came to know that it has been so much advances have been done.
Developments are going on constantly. We are not aware of them. That is why.
Yes, sir. You are right.
Just to make ourselves aware of so many developments all over the world.
Yes, sir. Definitely, certainly.
Nagaraj?
Yes, sir. Sir, Professor Rudraswamy, here you have covered almost all accelerators in the world and also especially in our state, Karnataka, including Bangalore University accelerator. In fact, you have also talked about what is that final strong focusing also, and including that synchro, cyclotron, tevatron, large hadron collider. I think to talk about each accelerator, it will take 1 or even more than 2 hours. Anyway, you have covered almost all accelerators, and including the Nobel Prize got for each one. Yeah, thank you very much, sir. And
Yes, sir.
definitely you must have taken at least more than 15 days to cover all these things. Thank you for your work and also
Thank you, sir. Thank you.
cover all those things.
Thank you very
Thank
much,
you
sir.
once again.
Thank
And
you,
in
sir.
this contact, let us also thank Gnanadhara, Dr. M.K. Raghavendra, who is supplying this platform. almost every Sunday. And Sai Venkataraman, he is doing that YouTube thing. And anyway, Professor Cogley is also catch hold of the persons every Sunday. And special thanks to Professor Dinesh Srivatsava. Maybe he is new to us. And anyway, he has attended our...
1 minute, Professor Srivastava is a distinguished scientist who is now at NIAS in Bangalore. And he has agreed to give a talk on 18th of May about climate change and all that. He is an expert in that field. Of course, originally he is a nuclear scientist, but he is now working in the area of climate change. So he has agreed to give a talk. He has written a book also, a very big book on climate change and what are the effects of climate change, how we arrive at climate change. So it will be very nice for us to hear from him about climate change. And he has kindly agreed to give a talk on May 18th. So he's a very senior, distinguished scientist, nuclear scientist of India.
Where he is located, sir, right now, sir? He's in
Bangalore. Now I'm at NIAS, Bangalore.
Yeah, NIAS, Bangalore.
So very good, sir. Very good. I think then we can have one talk in one of the colleges, like what he was telling yesterday, that he is going to give a talk in Mysore University. Like that, we can arrange from KPA in one of the colleges.
He likes that. He likes to talk in
offline talk only. Yes, let us go for online talk. After that, we can think of inviting him to give a talk offline in one of the colleges, sir. So thank you very much, sir, because of your presence in this talk. So thank you, one and all. And I think Professor Cogley has got an announcement to say for the next talk.
Next Sunday also, I fix a speaker. So he has yet to give me the exact title.
For the next talk, maybe I will ask one of the person from MVIT, sir, M. Vishweswaraya Technology College, Engineering College, Hariharan. He is interested to give a talk. I will find out and then let you know, sir.
Yeah, please confirm it soon so that...
okay, sir. I will have to talk to him again. Only next Sunday, it seems. Okay, then.
Professor Srivastava will contact you and then fix up the talk, sir.
Okay, sir.
Thank you very much.
Thank you very much, sir. Thank you, one and all.
Thank you.
Thank you, sir.
Take care.
Thank you, sir. Thank you, Professor Srivastava. Thank you very much, sir.